Hello, I'm going to discuss operational amplifiers and the best way to analyze the circuits. Hopefully it'll give you some insight and make them a little easier for you. I'm going to start out by looking at an ideal operational amplifier, and its symbol looks like this, and it's biased with a plus voltage, which they normally call VCC, and a negative VS voltage, which they normally call VEE. I want you to notice it has two inputs. It has an inverting input. The inverting input is the negative input. Remember that. It's something you just have to memorize. The inverting input is the negative input, and the non-inverting input is the positive input down here. The inverting input has a voltage that we're going to label V minus, and the non-inverting input has a voltage we're going to label V plus. The ideal operational amplifier has a current there we're going to call I minus, and that's equal to 0 amps. And it has a current going into the non-inverting input we're going to call I plus, and that's equal to 0 amperes. So I want you to realize that the ideal operational amplifier is not a current device. It does not run on current. It's a voltage operated device, and that's how we're going to use it when we analyze it here. And the input resistance looking in is equal to infinity ohms. So if you're out here and you're looking in, whether you're looking into the inverting operational amplifier input or the non-inverting operational amplifier input, the input in resistance that you see is infinity ohms. Therefore, that's what leads to the current on the negative input has to equal to the current on the positive input, and that's equal to 0 amperes. I will mention also that the ideal operational amplifier has an output resistance looking in to the operational amplifier like that. If you're on the output here and you're looking in, R out is equal to 0 ohms. And the open loop voltage gain without any resistors in this circuit, open loop, without any resistors being fed from the output back to the input, it's infinity. So there's the characteristics of the ideal operational amplifier, and that's what we're going to be using as we analyze these circuits and we go through the rest of these circuits. So let's take a look how we can analyze operational amplifiers and make it easy. If you take a look here at our first circuit, I don't want you to recognize these as an inverting operational amplifier or a non-inverting operational amplifier. For now, I just want to take a look, and I'm going to point out something. This R2 resistor, we're going to refer to it as a feedback resistor because it takes an output and it feeds back that output, a portion of that output in most cases, back to the negative input terminal, to the inverting input terminal. That's referred to as negative feedback. And most of your circuits are going to be negative feedback. You're not going to have positive feedback in most of your initial classes. So it takes a portion of the output voltage, in this case, and it feeds it back in this loop to the inverting input. That's called negative feedback. The whole reason for that resistor feeding the voltage back, and I don't tell you this, is to make the voltage at that point and this point identical. To make the voltage at the negative input and the voltage at the positive input, to make those identical. That's the whole purpose of this operational amplifier when you have feedback in. So keep that in mind, that all that feedback resistor is going to do is keep the voltage at this point and this point the same. And we're going to use that to analyze these circuits without classifying them as inverting or non-inverting op amps. So let me show you what I mean. We're going to make this a feedback resistor up here, RF. And I'm going to make this a 20K ohm resistor. I can make it anything. And there's R1, and I'm going to make that a 5K ohm resistor. And I'm going to say my VIN out here is 5 volts, just making up things. And I want you to take a look at that circuit. I want to calculate what V out is equal to. Do you know the voltage at this point absolutely at the V plus, or do you know the voltage at that point absolutely at the V plus? Well, I think you can look at that and say, well, this is your ground reference of 0 volts. So the only voltage you know for sure is that point there at the plus input, and that's 0 volts. You're going to project that over to here, and you're going to make that point 0 volts also. That's why that feedback resistor's in there. It's to make that happen. The op amp will make that happen. Once you project that voltage over to the other side, you can completely forget about the op amp. You can take it out of the circuit, and you can completely ignore it for calculation purposes. Incidentally, I want to point out at this time that when you do that, that point right there is called virtual ground. It's virtually ground. It's not ground, but it's virtual ground. They call it virtual ground. So once you do that, you can go back to the actual circuit, ignoring the op amp. Let's do that. Come over here, come up here, come over here, put in your 20K, put in your 5K, make this 0 volts, don't forget that projected voltage, make this 5 volts, come down here, and here's your V out that we want to calculate. Well, that's all you need to make a calculation on V out. I think you could see there that the voltage at this point right here is 5 volts, and the voltage at the right-hand side of the 5K resistor is 0 volts, so conventional current has to flow in that direction. And don't forget the passive sign convention, plus to minus. You always are going to have a voltage drop in the direction of current. Current always enters the positive terminal of a resistor and exits the negative terminal. That's a passive sign convention. You have to use it. So that current can't go into the op amp, don't forget up here, because the op amp, that current there is 0. Every bit of that current has to come up and go through that 20K. And it has to go in that direction. It can't change direction. If it's coming left to right through the 5K, the current has to continue left to right through the 20K, and its passive sign convention puts a plus on the left side of the 20K and a negative on the right. So first thing you want to do is calculate the current I, the current through the 5K resistor right there. Well, a quick calculation says the current through the 5K resistor is equal to the voltage on the positive side, which is 5, minus the voltage on the negative side, which is your virtual ground point, 0. And you're going to divide that by 5K. I think you can see that that's 1 milliamp. And every bit of that 1 milliamp, let's change color here, every bit of that 1 milliamp has to flow up to there, up through the 1K. So you can calculate the voltage through that 20K. You can calculate voltage across the 20K ohm resistor now, which is simply the current I, 5K, it's the same current, times the 20K ohm resistor. That's going to be equal to the 1 milliamp times the 20K, and that's equal to 1 milliamp times the 20K is equal to 20 volts. But take a look. That's the voltage across the 20K resistor. That is a drop from the left side to the right side, that's a drop of 20 volts. Look at the polarity up there. So now you can calculate voltage out. You can say voltage out is, what voltage do you know? Well, you know the voltage on the left side. It's 0 volts. And you're subtracting the 20 volts. So you end up with a negative 20 volts for the output voltage. And that's your answer. And we made that calculation by ignoring the operational amplifier once we projected the virtual ground point over to the other side. Again, some of you are going to recognize the fact on this circuit that it's a non-inverting, it's an inverting amplifier circuit. So you're going to recognize it's an inverting op amp. Because the voltage is going indirectly to the negative input. That's an inverting op amp. And you know that the gain of an inverting op amp is negative RF over R1. So if you take that, you're going to put in your values. You have a negative 20K over 5K. You're going to get negative 4. So you get a gain of negative 4. Therefore, your V out has to equal your input voltage times your voltage gain. It's a multiplier. So you can see your output voltage in this case is going to be equal to the input, which is 5, times your negative 4. So you see you get your negative 20 volts. Okay? So why did I show you all this down here? Why did I show you all that? Because I wanted to show you in a simple circuit how, when the circuits get complicated and more complicated, and you can't pick out a gain equation real easy, you can always analyze it through a projection. That's why I wanted to show you the technique. So let's take a look at problem number 2. Do it the same way. See how we can analyze this real quick. Again, I'm not going to classify this as inverting amplifier, a non-inverting amplifier. I mean, some of you will recognize that, gee whiz, we could take the 3 volts and we could reduce the 1 volt to 0 by shorting it, and we could find V out prime, and then we could find V out double prime by using the 1 volt and shorting out the 3 volts, and that's called superposition. And you could do that. But I'm showing you the other technique where what voltage do you know for sure in that circuit? Do you know the voltage at this point right here for sure, or do you know the voltage at that point right there for sure, at this point up there? Well, if this is 0 volts down here, you know for a fact that the voltage on the plus input right here is up 1 volt, is 1 volt. You project that 1 volt over to here. When you do that, you can get rid of all this op amp circuit. Once the projection is complete, you can get rid of all that. And then you just have this. You have 3 volts coming in. You have your 4K ohm resistor. You have your 1 volt right here. You come up, you come over here, and you go through your 10K ohm resistor. You come down here, and here's your V out. And that's what you want to find. With that information right there, you should be able to find V out ignoring the op amp once you projected the voltage. So how do you do that? Well, just taking a look, using Ohm's law here, I know that current has to go from the more positive voltage to the more negative voltage. Current has to flow through the 4K resistor left to right, because 3 volts is greater than 1 volt. That puts a passive sign convention of plus on the left, obviously, and minus on the right. So I can make a calculation for that current through the 4K ohm resistor. The current through the 4K ohm resistor has to equal the voltage on the plus side, which is 3, minus the voltage on the negative side, which is 1, divided by 4K. And if you take a look at that, that's 0.5 milliamps. Every bit of that 0.5 milliamps has to come up and go through the 10K resistor. We're ignoring the op amp. You know why? Because no current goes in there. Remember? There's no current that goes into the op amp. There's no amps that flow in that direction. So every bit of that current has to go through the 10K. And it can't change direction, so it has to go plus to minus using the passive sign convention. So if you calculate the voltage across the 10K ohm resistor, it's equal to the current gone through it times the value of resistance. So the current gone through it is 0.5 milliamps. And you're going to take that times your 10K. So you make a calculation there, and you're going to get 5 volts. That 5 volts is the voltage that's going to be across that 10K resistor. But look, it's a drop. You're going from a more positive on the left to negative on the right. So now you can calculate V out by simply saying you know the voltage absolutely on the left side of the 10K resistor. It's 1 volt. It's not virtual ground like the last problem. The voltage on the left side of that 10K resistor is 1 volt. That's your reference point now, 1 volt. And then you're subtracting the voltage across the 10K because it's a drop plus to minus. And you make a calculation there of negative 4 volts. And that's your answer to that problem. By simply ignoring the operational amplifier once you make a projection. Those of you that make the superposition calculation, you're going to see you'll get the exact same answer. And then finally, let's take a look at this problem here and see how you make a calculation on this using my method. Some of you will recognize this is a non-inverting operational amplifier circuit, and you'll just use the gain equation and you'll get the answer. But for those of you that don't, let's see. Do you know the voltage at this point absolutely, or do you know the voltage at this point absolutely? Well, you don't know the voltage down at that point because V out's the unknown, and you can't use a voltage divider to find the voltage at that point using V out. You can't say, you can say the voltage at the V minus input is V out times 2K divided by 7K. That's a valid calculation, but it doesn't help you because you don't know V out. You're trying to find V out. The only voltage you know for sure in that circuit is the voltage right there, and that's the voltage at the V plus input. You know that voltage right there, absolutely. The reason you know it is because looking in here, that looks like an infinity resistance. It looks like an open circuit, remember? It doesn't take any current. So all you have is a simple voltage divider rule to find V plus. It's a simple series circuit. So V plus is simply equal to the total voltage, which is 3, times the 8K divided by the 4K plus the 8K. Since you know all that, you can simply make the calculation. And that gives you the voltage at the plus input. And that's equal to 2 volts. Now that's the voltage here. That's the voltage at this point. That is the 2 volts. That's the voltage you would use to multiply times the gain equation for some of you to get the output voltage. But we're not doing it that way. We're projecting that over to the other side. We're going to project that 2 volts at that point to the other side, which places it right down here, same point, at 2 volts. And then we're completely ignoring the op amp. So what do we have to look at that point? Well, let's redraw it. We have a 2K that goes to ground. We have a 5K, which was the feedback resistor. Then we come up, and here's your V out. And the only thing we know is that voltage right there is 2 volts. We completely ignored the op amp. We got the 2 volts projected. Now, we should be able to calculate V out with no problem there. How are you going to calculate V out there with no problem? Well, what do you know? Well, you know this current right here. You know that current right there. So the current in the 2K ohm resistor is equal to 2 volts, which is the voltage on the plus side, minus 0 volts, because that's the voltage on the negative side. Don't forget the passive sign convention, plus at the top, negative at the bottom. Current's going to flow down, you know that for sure. It's gone from more positive voltage, plus 2, down to 0 volts. And you divide that by 2K. That's going to equal your 1 milliamp. So you know you have 1 milliamp flow in there. Now, how does that 1 milliamp help you analyze the circuit? Well, that 1 milliamp has to come from up here. It has to go in that direction, in that direction, in that direction. It's the same current. Because don't forget, we're ignoring the op amp because it's no current. There's no current here. That current right there is 0. So I can calculate, or I can find the polarity. You know the polarity is plus to minus. There's your passive sign convention. So you know that the voltage across the 5K ohm resistor is equal to the current, I, times the 5K. That's 1 milliamp times 5K. So you see there, that's pretty easy. That gives you 5 volts. That's the voltage across that resistor. So how do you find V out? Well, I just start at the voltage you know. Let's start at reference point. Let's start down here at the bottom. So V out is equal to, you're starting at a reference point 0. Then you're adding the 2 volts because you're up 2 volts. When you go up through the 2K, you're 2 volts up. You're stepping up in voltage. And then you go up another 5 volts. Look at the polarity. That's equal to 7 volts. And that's your answer to that problem. And I think you could see that if you take your 2 volts and you take it times a gain of 1 plus RF over R1, you're going to get the same plus 7 volts. But we're not doing it that way. We're doing a projection. So it's plus 7 volts is your answer. In passing, all I want to say is this. I give this to my students and I say that analyzing negative feedback operational amplifier circuits. If you can identify an op amp circuit as one of the 3 simple configurations discussed in class, and I'm sure you have, just use the gain equations as shown in the previous examples. And there's your gain equations you use when you recognize that. However, if the circuit is more complex, the procedure below is key to analyzing most circuits, and that is really what I've been doing. I've really been doing nodal analysis without telling you, but that's how you can ignore the operational amplifier. I hope that this video lecture on op amps made easy helps you understand them a lot better.